So what we're going to do is we're going to go in and we're going to reconstruct this shear force and bending moment diagram using these rules. And I already know the answer, so I'm just going to work on top of that. So I'm going to sketch over top of what we solved for the other day. But presumably you would come in without having anything on our shear force and bending moment diagram. Now, typically I'll go in and sketch these lines in here. I've got them sketched in as dashed lines here. When I've been working on recordings to post on YouTube, I've been using green construction lines like you guys learned in either your drafting class or in your architectural skills classes, depending on your program. So what we're going to do is we're going to solve for the beam reactions. We'll assume that you guys can do that. We'll assume that they're given to us here. So we have a reaction at the left end of 8.9 kips, a reaction at point C of 26.1 kips. Okay, step 2, we're going to work from left to right. So we're going to start off the left end of the beam where we have a 0 shear force. So that's a pinned end. So if we move off to the left of that pin, the shear is 0. Okay, so when we move to the right from just off the left end of the beam, the first thing that we do is we encounter a concentrated load. So rule number 7 says that when we have a concentrated load acting on the beam, it causes an instantaneous change in shear. That change in shear is equal to the magnitude of the load. So that load points upwards. So the shear just to the right of that point is equal to the shear just to the left of that point, plus the change in shear. So just to the right of that point, we end up with a shear force of 8.929 kips. All right, next we're going to be moving left to right. There are no external forces on the beam between points A and B, so nothing happens on the shear force diagram between points A and B. All right, we just move over like that. At point B, we encounter a concentrated force. So this creates an instantaneous change in the shear force diagram with the change in shear equal to the magnitude of the load. The load points downwards, so the change in shear is equal to negative 25 kips. The shear to the left of point B was 8.9 kips. We have a change in shear equal to minus 25 kips. So then the shear force to the right of point B is equal to minus 16.07 kips. Then between points B and C, there's nothing happening on the beam. There's no externally applied forces, no reaction forces, so nothing happens. So we just have a constant shear between those 2 point loads. Then when we hit point C, we encounter an upwards force there. It's a reaction force, but it doesn't matter if it's an externally applied load or whether it's a reaction force. It's still a load on the beam. We have a change in shear, and so the shear just to the right of point C is equal to the shear just to the left of point C, plus the change in shear at point C. So we started off just to the left with a shear of negative 16. We have a concentrated force of 26, and so we end up just to the right of point C with a shear force equal to 10 kips. Okay, there aren't any externally applied loads between points C and D, so there's no change in shear between points C and D. At point D, we have a concentrated force acting downwards. So that means that just to the left of point D, we had a shear of positive 10. The shear force just to the right of point D is equal to the shear force just to the left of point D, plus the change in shear at point D. So we end up with a 0 shear force there. So check number 10, step number 10 is we need to check to make sure that the shear force diagram closes. If you don't end up starting at 0 and ending at 0, then something went wrong. You either screwed up drawing the shear force diagram or the reactions that you had on your beam were incorrect. Okay, step number 11, we check rule number 3, the shear at the free end at point D is equal to 0. So that checks out and everything is good and everyone is happy. Okay, no questions in the chat window. All right, moving on then. Now that we have our shear force diagram constructed in its entirety, then we'll go on and sketch our shear force diagram, bending moment diagram rather. All right, so clear the slate. We start off the left end of the beam. We work left to right, always left to right, never right to left. We always work left to right. So we start off the end of the beam. The moment at the pinned end A is equal to 0. Okay, so start with 0 moment off the left end of the beam. encounter a concentrated force acting upwards. So that concentrated force acting upwards creates a kink in our bending moment diagram. It was horizontal just off the left of the beam. It kinks and it creates a kink at point A. Now, using rule number 10, the change in bending moment between points A and B is equal to the area under the shear force diagram between those 2 points. So what's the area under the shear force diagram? It's basically that area there that's shaded in as red. Now we can calculate that area. It's just a rectangle, right? So it has a height of 8.929 kips and it has a width of 14 feet. So that gives us a moment of 125 kip feet. So that means that the change in moment is equal to that area. It's equal to a positive 125 kip feet. So the moment at A is equal to 0. Therefore, the moment at B is equal to the moment at A plus the change in moment between A and B. So therefore, at B, we have a moment of 125 kip feet. All right. Now, the bending moment diagram in this region is linear. In order to get from shear to bending moment, we integrate, right? If we go back to our cheat sheet, we would see that dm dx is equal to v. So the slope of the bending moment diagram is equal to the magnitude of shear. So the magnitude of shear between points A and B is 8.9. So that means that the magnitude of the shear force is, the slope of the bending moment diagram is 8.929 kips. All right, that means that if we have a constant curve for shear in that region, a 0th order curve, if you will, then we have a 1st order curve in moment. So we integrate a 0th order curve in the shear to get to the 1st order curve in moment. All right, step number 5, moving left to right, we encounter a concentrated force acting upwards. It's actually downwards. I wonder how many times I've made that mistake. Concentrated force acting downwards at point B. And I'll circle that and go back and fix that after the fact. At point B, this creates a kink in the bending moment diagram. Okay, using rule 10, the change in bending moment diagram between points B and C is equal to the area under the shear force diagram between those 2 points. So that area is shaded in there. The area under the shear force diagram between B and C is equal to a negative 16 kips acting over 14 feet. So we go from a moment at B of 125 kip feet to a moment at C equal to 125 minus 225 equals minus 100. So that takes us down to that point. Excuse me. Okay, we're integrating a constant shear force, so we end up with a linear bending moment diagram. Okay, clear the slate. Okay, moving left to right, we encounter a concentrated force acting upwards at point C. That's correct. So that creates a kink in the bending moment diagram. So moving left to right, rule number 10, the change in bending moment between points C and D is equal to the area under the shear force diagram between B and C, between C and D. So in this region, we have an area under the shear force diagram equal to 10 kips times 10 feet, or equal to a positive 100 kip feet. So the moment at D is equal to the moment at C plus the change in moment between C and D, or the moment at point D is equal to 0. Okay, the bending moment diagram in that region is linear because we integrate a 0th order shear force curve to get to a 1st order bending moment curve. Okay, rule number 7, that creates a concentrated load of 10 kips, creates a kink in the bending moment diagram in that region. And then we check to make sure that the bending moment diagram closes. If it doesn't, then you screwed up drawing the bending moment diagram, or you screwed up when you had your shear force diagram. And then finally, we check rule number 5, the moment at point A is equal to 0. It's the moment at the free end of a beam. And then the moment at point A is 0 because it's a pinned end. Moment at point D is 0 because it's a free end. All right, so we went through and we sketched the shear force and the bending moment diagram using rules. It might not seem like it right now, but this method is a lot faster than using the brute force method where you go through and cut sections. I've gone through it with quite a bit of tedium here, going through with a lot of detail. Once you get better at doing this, you've drawn about a dozen or 500, then you get a lot faster to the point where you can sketch a shear force and bending moment diagram for a beam like this in about 3 or 4 minutes. All right, so we still have one thing to check though. There's an inflection point in this beam. So there's a point where the bending moment stops being positive and starts being negative. It's often we want to know where that occurs. It's not sufficient to know that it occurs somewhere between point B and point C. We need to know exactly where that happens. So what we're going to do next is we're going to go in and figure out how to solve for the location of that inflection point. So we know that the moment at point B is equal to 125 kip feet. Okay, we're going to define this distance x as the distance between point B and the inflection point. So we'll define distance x like that. We'll call that point I for inflection, or in some of the examples I've worked out earlier today to post on YouTube, I called it the IP inflection point. So that distance x is measured from B to the point I. Now we know that the moment at I is equal to the moment at B plus the change in moment between points B and I. But we also know that if that's an inflection point, that moment at that point has to be equal to 0. So what we can do is substitute in here, and we could say that rule number 10, the change in moment between points B and I is equal to the area under the shear force diagram between points B and I. So we know that that area is going to be equal to minus 16 kips multiplied by this distance x. So if we substitute that into our equation, we could say that the moment at I is equal to 125 kip feet plus a negative 16 times x is equal to 0. So now you can solve for that dimension x, and you can find out that the inflection point occurs at a distance of 7.778 feet from point B. All right, and then that would be important to us because we would know that at that point we would need to reinforce the bottom of a concrete beam with rebar to the left of that point. We would need to reinforce the top of a reinforced concrete beam with rebar to the right of that point. So we know that tension is on the bottom for a positive moment to the left of the inflection point. We know that tension is on top for a negative moment to the right of that point. So that's why we do